On this assignment, we'll be primarily focused on confidence intervals for the difference of two means. We will practice some match pairs later, which is a mean of differences, but this one's focused on the difference of means. So in a study aimed at reducing developmental problems in low birth weight, under 2,500 grams babies, the Journal of the American Medical Association, so that's where it was published, 347 infants were exposed to a special education curriculum, while 561 did not receive any help. After 3 years, the children exposed to the special curriculum showed a mean IQ of 93.5 with a standard deviation of 19.1. The other children had a mean IQ of 84.5 with a standard deviation of 19.9. Find a 95% confidence interval estimate for the difference in mean IQ of low birth weight babies who receive special intervention and those who do not. So our confidence interval is our statistic plus or minus our critical value. And so we're going to have to find our statistic will actually be, as you can see, they already have all the same values there. So we don't really have to check that. It is the 93.5 minus the 84.5. We are going to have to find our critical value. And the way we do that is because we're dealing with means, we're using the t distribution. And it's going to be inverse t. Now, I want a 95% area in the center, but that leaves 5% left over, which I have to split between the two ends. Inverse t only does left-handed area. It won't just do center. So I'm going to add that 0.025 to the 0.95. And then for degrees of freedom, because I'm using two samples, we use the conservative rule. We take the smaller sample size and subtract 1. So to find the critical value, we go second distribution. And if it was a z-star critical value, like for proportions, we would use inverse norm. But since we're dealing with t's, which is basically means, it's inverse t. And we have to do a slight adjustment to our area because we're not doing center area, we're doing left area, also known as percentile. So I have 0.95 would be the center, that leaves 5% left over. If I split it, it's 0.95 plus the 0.025 to the left of it. And then my degrees of freedom, just pick your smallest sample area and that, sample size, I should say, and just take 1 away from that and hit enter. And there you go, 1.966 or 1.97. So now we know that our critical value is 1.97, which eliminates 3 of the options down below. So we're just deciding between the top 2. So then I pull the equation for standard deviation. And as you can see, we basically take our standard deviations for the samples, right? So I have, there it is, 19.1. I'll square that and put that on top. 19.9 goes here. 347 goes down here. And 561 goes down there. So it is choice A. Number 2, does socioeconomic status relate to age at time of HIV infection? For 274 high-income HIV-positive individuals, the average age of infection was 33 years, with a standard deviation of 6.3. While for 90 low-income individuals, the average age was 28.6 with a standard deviation of 6.3. Find a 90% confidence interval estimate for the difference in ages of high and low-income people at the time of HIV infection. So again, we're going to do the same thing we did on the last problem. We have our statistics here. And if I take the difference, I get 4.4. So you can see that 30.8 and D and E are not the correct answer. Then I'm going to go ahead and find the critical value. We're doing a 90% confidence interval. So the center area is 0.90. I have 10% left over. Cut that in half. That's 0.05. And the smallest sample size is 90. So degrees of freedom is 90 minus 1. So we're going to find the critical value again. If we're doing proportions, it would be inverse norm, but we're doing mean, so it's inverse t. And last time we did a 95% confidence interval. This time we're doing 90%. But since it's left area only, I have to add half back of the missing area. So the full area I was missing was 10%, so I have to add back 5%. Then we go and we pick the smallest sample size, which in this case is 90, and subtract 1 from that, and calculate. And we get 1.662. So now we know our critical value is 1.66, which is probably good enough. And then we need to find our standard error. And substituting in, we get the 6.3 is the same standard deviation for both. We have both sample sizes underneath. Kind of plug and chug on the calculator, and we get a standard error of 0.765. And then if we substitute those two values in, our critical value and the standard error, we get 1.27, which leaves us with choice B. But there is, in a way, an alternative method to do this problem. Okay, so we calculated everything by hand, which is fantastic, but there could be a shorter way to do this. So what we're going to do is we're going to create a 2-sample t interval. So we're 2-sample, and we've got to make sure it's a t interval. There it is, 2-samp t int, and hit enter. And you can see we can either do stats or data. Since we have the stats, we'll stay here. X bar 1 is 33. Standard deviation is the same for both of them. 274 for this first sample. 28.6, 6.3, and 90. Then they ask us the confidence level, and we go 0.90. Now, by the way, you're going to see this pooled option. We never jump into the pool because there's no reason to think, even though on our samples are the same, that our standard deviation is the same. So we're going to go ahead and calculate it. And you see it's going to come up with a slightly different value. Here's the degrees of freedom using technology. So technology is actually recommended for doing this because we use the conservative rule to come up with our t-star. But it actually does a very fancy calculation, which I'm not going to go into the math, and it figures out your new degrees of freedom. So we can use this to actually go ahead and figure out our margin of error. So we have 5.67 I'll use, since most of these are going 2 decimal places, minus 3.13. 5.67 minus 3.13. So that, and then I divide that by 2. That is the half width, or the margin of error. If you want to know what the midpoint is, you can say 5.63 plus 3.13 and take the average. Make sure you add them before you divide by 2. And that is your midpoint. It doesn't exactly match ours, but it's close enough. 4.38 rounds to 4.4. So that is a shortcut way to find your midpoint and your margin of error. So there's the 1.27, your margin of error, using the calculator. And I just realized I did 5.63 instead of 5.67, which is why my answer is slightly off from the 4.4. Number 3, an engineer wishes to determine the difference in life expectancies of 2 brands of batteries. Suppose the standard deviation of each brand is 4.5 hours. How large a sample, same number of each, type of battery should be taken if the engineer wishes to be 90% certain of knowing the difference in life expectancies to within 1 hour. So here's all the data that I wrote down. We have our standard deviation for the sample, our margin of error, our confidence level, and we're trying to figure out N. So our margin of error is our critical value. We're going to use C star to basically, we're just going to do one round with Z star. If you wanted to be extra sure, you could actually go back and do another round with a T star. So if we're using Z, the reason I use Z star is to find a T star, I need degrees of freedom. So I have to use the inverse norm. I'm sorry, I wrote inverse C, but it's inverse norm. And so the area is 0.90, and we want the center area, it's 1.645. So you should probably have that memorized already. So now when I substitute into the margin of error equals the critical value times the standard error for the sample, we get 1 equals 1.645. So the 1 is the margin of error. 1.645 is the critical value. And then I'm using the formula for standard error from your math chart. So I get 1.645 times times square root of 20.25 over n plus another 20.25 over n, which is basically 40.5. And then I square everything, which gives me 1 equals 109.6 over n. Solve for n, and I get 109.6. So my answer is D. Number 4. A school superintendent must make a decision whether or not to cancel school because of a threatening snowstorm. What would the results be of type 1 and type 2 errors for the null hypothesis? The weather will remain dry. So type 1, H0 is true, the weather is dry, but we think HA is true, so we cancel school. So the weather remains dry, but school is needlessly canceled is type 1. Type 2 would be, type 2 is that the other one is true, that the weather will not be dry, that we should cancel school, but we don't. So don't cancel school, but the snowstorm hits. B. Number 5. A bank wishes to survey its customers. A decision is made to randomly pick 10 customers who just have checking accounts, 10 who have savings accounts, and 10 who have both checking and savings. This procedure is an example of what type of sampling? Well, these are different types of groups. So we're taking a sample from each group. This is called stratified sampling. Number 6. A histogram of education level and numbers of years of schooling of the adult population of the United States would probably have which of the following? Well, usually students tend to stop or continue at 8th grade, high school, graduation, and 4 years of college. So you'd probably see clusters at 8, 12, and 16. Number 7. Given a random variable x takes 3 possible values, x1, x2, and x3, which of the following statements must be true? Well, first of all, these are not probabilities. These are outcomes. So it's not A or B. All right. C looks more like standard deviation, and that uses probabilities as well, so it's not that one. Expected value usually plays well. That one should be fine, whereas a multiplicative constant is squared for variance, so it is not E. So the correct answer is D. Number 8. A confidence interval estimate is determined from the summer earnings of an SRS of n students. All other things being equal, which of the following will result in a smaller margin of error? So, a higher confidence level means a larger margin of error, so it's not A. A larger sample standard deviation means a larger margin of error, so it's not B. A larger sample size should reduce the margin of error because it tightens up your standard error. D, less precision means a wider interval, it's not D. And then while bias doesn't really affect the margin of error, it's not a good thing. So we're going to go with choice C. Number 9. Suppose a retailer knows that the mean number of broken eggs per carton is 0.3 with a standard deviation of 0.18. In a shipment of 100 cartons, what is the expected number of broken eggs and what is the standard deviation? Assume independence between cartons. So first of all, we are looking at a shipment, which is a combination of 100 different cartons. So we have carton 1 plus carton 2 plus all the way to carton 100. The expected value for Y is the expected value for the first carton plus the second all the way to the 100th. The expected values are the same, so I can just say, oh, that's just 100 times the expected value of X, or 100 times 0.3, which is 30. Variance works similarly. We have variance of Y is going to be the variance of the first carton plus the second all the way to the 100th. Since they're all the same variance that we expect, I can say that's 100 times the variance of X. Now, the variance of X is just the standard deviation of X squared, so I'm going to take that 0.18 and square it. Then multiplying that by 100, I get 3.24. And then to go backwards to standard deviation, I need to take the square root of the variance, and I get square root of 3.24 is 1.8, so my answer is B. Number 10, a computer technician notes that 40% of computers fail because of the hard drive, 25% because of the monitor, 20% because of a disk drive, and 15% because of the microprocessor. So this is not talking probabilities on a brand new computer and the component's going to be failing. This is all broken computers, and he has all the reasons they fail. They appear to be mutually exclusive. They add up to 100%. So the probability that it's a hard drive, given that it's not the monitor, right? That's basically, so we know that the problem with this computer is not the monitor. So what is the probability it's the hard drive? Well, I take the probability that it's just the hard drive, which is 0.40, and then I take all the other probabilities except for the monitor, and that's the bottom. And when you add them up and divide, you get 0.5333, or choice D. Number 11. If all the other variables remain constant, which of the following will increase the power of a hypothesis test? Well, number one, increasing the sample size tightens up distributions and increases power. So 1 is true. Increasing significance level makes it easier to reject H0 and increases power. 2 is true. Increasing the probability of a type 2 error, which is beta, well, power is 1 minus beta, so increasing beta decreases power, so 3 is false. And if you forgot about these, we also went through this in our last activity on hypothesis testing with proportions too. So you might go ahead and take a look at that. So our correct answer is 1 and 2, choice D. Number 12. An engineer wishes to determine the quantity of heat being generated by a particular component. If she knows that the standard deviation is 2.4, how many of these components should she consider to be 99% sure of knowing the mean quantity to within plus or minus 0.6? So we have our standard deviation, we have our margin of error, our confidence level, and we're trying to determine sample size. So we're going to have to come back to this puppy right here. Margin of error equals your critical value times your standard error. Well, our critical value, we're going to use Z because we don't have a sample size to do T. So we have center area is 0.99, right? And we get 2.576. So I'm not going to show you the calculator this time. Hopefully you know how to do it. Okay. So we substitute in 0.64 ME, 2.576 here, and then this one we have to take the formula where we divide by square root of sample size. Now I'm going to go ahead and multiply these two together, and then basically cross multiply, and then go ahead and divide these two out. So square root of n is 10.304. If I square it, I get 106.17. Even though this is low, we always round up if it's not an integer, so our answer choice is C. Number 13, a company that produces facial tissues continually monitors tissue strength. If the mean strength from the sample data drops below a certain level, the production process is halted and the machinery is inspected. Which of the following would result from a type 1 error? So a type 1 error means the null is true. The tissue strength is fine. We should assume the machinery is working. But we think the alternate is true. We think the strength is low and we halt production. So we halt the production process while the tissue strength is still within specifications. Number 14, suppose that our null hypothesis P equals 0.6 and the power of the test for our alternate P equals 0.7. By the way, that's a very unusual alternate, but okay, is 0.8. Which of the following is a valid conclusion? Well, I see we're talking a probability of type 1 error. That's alpha, and we don't know what it is. If the alternate is true, the probability of failing to reject H0 is 0.2. So that's beta. Let's go ahead and calculate it. Power is 1 minus beta, so that's probability of type 2 error. We know the power is 0.8, and so 0.8 equals 1 minus beta, so beta must be 0.2. So that is the probability of a type 2 error, which tells you that C is not correct, B is correct. Number 15. The distribution of weights of 16-ounce bags of a particular brand of potato chips is approximately normal with a standard deviation of 0.28 ounces. How does the weight of a bag at the 40th percentile compare with the mean weight? So we're talking about individuals here, so this is just plain old normal distributions. And my mean is 16, and my standard deviation is 0.28, right? That's my model. So I need to find what is the cutoff value with 40% of the area to the left. So you can see I did find it here with the stapplet, but this is how we find it on the calculator. Value equals inverse norm. The area is going to be 0.4. The mean is 16, and the standard deviation is 0.28, and we're looking at left area. So to find the value on the calculator, we hit second distribution, and instead of doing normal CDF, that's probability, we're doing inverse norm. And we want our area to be 0.4. Our mean is 16. Our standard deviation is 0.28. And we want the left area because it's in the 40th percentile. And hit enter. And voila, 15.93. So we have our values 15.93, and we want to know the difference between that and the mean. I went ahead and just said the mean minus the value, which is 0.07, but we also know it's below the mean, right? Because our mean is 16, so our answer is D.